is not available. Hira Khanum. Now I am going for Zeeshan Ali. Zeeshan Ali, you are here. Zeeshan Ali, you are here.
Yes, 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 sir. Yes, sir.
Zeeshan Ali is a Professor of Excellence in Resources Engineering from UT Lahore, and he is going to present future stream flow prediction of Astor River Basin using UBC Watershed Model. Zeeshan Ali, please. Now
Yes,
you
sir.
can
Thank you, sir.
begin.
Bismillah Rahman Rahim. Research topic is future stream flow prediction of Store River Basin using University of British Columbia Watershed Model. Here is the presentation outlines, introductions, objectives, study area, methodology, results, and conclusion. Introduction is the availability of catchment water sources is closely linked to the variation in climate, and the global climate models have been used as a primary tool for examining the past and future changes in climate extremes. In Pakistan, the Indus River Basin covers around 520,000 kilometers squares or 65% of territory. Very roughly, at least 300 million peoples are estimated to live in the Indus Basin. As the population living downstream and other economic activities are highly dependent on these water sources, so it is vital to assess the water sources in this basin will behave under future climate change scenarios. The objective of studies was to predict the future stream flows in Store River basins, and the second objective is to evaluate the climate change impacts on hydrological process in Store River basin. This is our study areas, including 3 climatic stations and 1 hydrological stations. Dunya located at between 35 to 36 north and 74 to 75 east, with drainage area is 3,992 kilometers squares. About 16% of the area is covered with glaciers, with minimum elevation 1,178 to 8,054 meters. The annual and mean temperature during 1998 to 2012 was 9.9 degrees centigrade at Rattu and 2.9 degree at Rama, studied by Tahir et al. This is our methodologies and data collections, including observation data obtained from meteorological departments, WAPDA and GMRCs, while dam land use glaciers and GCM's global circulation models was downloaded from CMIP6 websites, while dam at 30-meter resolutions are obtained from Earth data, NASA websites, while land use and glaciers are obtained from globals and GLISM's sites. The data processing at the right side, UBC input preparations. This is a watershed model used for prediction of stream flows, while on GCM's data was obtained from given websites, and the data extracted by using GIS and MATLAB coding for both historical and futures. The historical data is as same data period as with observations. The change factor method is used to correct the data, and at last by using preparation of VAT files, number of parameters including almost 90 parameters are used to prepare VAT files, and at last the objectives are climate change impact on hydrological processes are obtained. These are the data collections obtained from different departments, including PMD, GMRCs, and WAPTA. While downloading GCM data of 3 climatic models, BCC, INM, and MPI of 3 variables, precipitation, temperature maximum, and temperature minimum was obtained under 3 different scenarios, including SSP 2.6, 4.5, and 8.5. The high resolution of 100 kilometer on daily basis for the period of 1995 to 2014 and for future 2020 to 2070 has been downloaded. These are the land use, glacier data, and zones and dam elevations processing in ArcGIS for the preparations of UBC inputs, land use, land cover, and how much glaciers. These all are used in the preparation of VAT file for UBC input models. By correction of the data by using by correction change factor method was used to convert a core scale data of 100 kilometer resolutions to point scale data. For temperature and precipitation, equations are given below. These are the UBC watershed models. Is a hydrological models designed for forecasting runoff from mountainous watershed, and daily and hourly point values data of precipitation and maximum and minimum temperature can be used as input to calculate the stream flow, while output includes daily discharge from rainfall runoff, glacier melts, and snow melts. The study area was divided into 7 different elevation bands, and model parameters are set within each bands. These are the flow charts generally used for the UBC watershed model. Here results. The calibration of UBC watershed model was done for the periods of 200 to 204 on the daily basis, and the efficiency coefficient of efficiency and coefficient of determination was obtained is about 0.82, while the validate data model can be validated for the period of 2005 to 2009, and its coefficient of efficiency and coefficient of determination is 0.83 and 0.84. These are the some number of parameters. Almost 90 parameters are used in UBC watershed model, but some of the sensitive parameters for climatic and geophysical characteristics of watersheds are used. Best suited values are included. These are the coefficient of determination between observed and bias corrected GCM data of 3 GCMs at Astor, Rama, and Ratu. MPI ESM1 to HR shows better results, followed by INM-CM5 and BCC CSM2 MR. But with precipitation range is 70 to 76, and maximum temperature range is 0.92, sorry, and minimum temperature is 0.90 to 0.91. Similarly, as followed by INM and BCC. These are the climate change impact on stream flow. Future stream flow under SSP 2.6 of MPI shows a little bit increasing trends, as similarly 4.5 also show increasing trend, but significant changing in trend under SSP 8.5. Similarly, INM-CM5 under SSP 2.6, 4.5, and 8.5 also show increasing trends, with significant increase under SSP 8.5 and with little change under SSP 2.6 and 4.5. PCC-CSM2-MR of SSP 2.6 shows decreasing trend, while on SSP 4.5 and 8.5 shows increasing trend. The relative stream flow changes compared with observational data periods for the period of 1990 to 2014 was obtained from SWHP was 149.35 cubics, as compared with future data for 2020 to 2017 obtained from GCMs. BCC shows significant decreasing trend, -1 to -3% under all scenarios, while INM shows large decreasing trend from -6 to -11%, while MPI shows -7 to -9% as compared to observed data. These are the climate change impact on hydrological process. Mean annual flow under SSP 2.6 of and 4.5 and SSP 8.5 of BCC-CSM2 MR shows maximum flow as compared to MPI and INM. The INM shows minimum flows, stream flows, and MPI is intermediate between BCC and INM CM5. Remainings are the rainfall outflow, snow melt outflow, glacier contribution, and groundwaters are the components. The sum of the all 4 components may be is equal to the mean annual flow of 143.65 for BCC. Similarly for all other models. This is the flow contributions in runoff. All GCMs shows increasing glacier contributions and rainfall outflow at SSP 2.6, SSP 4.5, and SSP 8.5, as BCC under SSP 2.6 shows 2.81, while under 4.5 shows 2.95. Similarly,
Excuse me,
for
Zeeshan.
yes, sir.
Zeeshan, no, we are a bit late. You can conclude your presentation.
Yes, sir. Conclusion: maximum stream flow generated under SSP 8.5 followed by SSP 4.5 and SSP 2.6 of selected GCMs. The stream flow contribution by snowmelt and groundwater remained toward decreasing, while contribution of rainfall and glacier remained toward increasing. Relative stream flow changes as the hydrological response show flows are decreased up to 3 to 11%, to 2 to 9%, 1 to 7% by SSP 2.6, 4.5 and 8.5 as compared with control periods. Thank you, sir.
Thank you very much, Zeeshan.